You've probably heard the phrase light year before. It's one of those space terms that gets thrown around in every documentary, every science video, every dramatic headline about stars exploding or galaxies colliding. But tonight, I want to ask you something simple. Do you actually know what it means? Not just the technical definition, distance light travels in a year, but what it feels like, what it really implies. Because once you actually understand what a light year represents, it breaks something in your brain, not in a bad way, but in a way that never quite goes back to normal. It's like realizing, for the first time, that time isn't the ticking of a clock but the movement of matter in space, or that the stars you see twinkling above you aren't just far away, they're impossibly far, impossibly ancient, and in some cases already gone. Let's start small. You live inside a reality scaled for your size. Your legs know the distance to the kitchen. Your mind knows the time it takes to walk to the corner store. A kilometer? That's a 10-minute stroll. 5 kilometers? You might drive. 50? Now we're talking a road trip. These distances fit inside your life. You can plan for them. You can feel them. If I tell you that your destination is 100 kilometers away, your brain automatically runs the math. Okay, that's maybe a 2-hour drive. Gas, snacks, a break halfway. Let's go. This is the world evolution prepared you for. We were shaped by the savannah, by the next waterhole, the next mountain pass, the predator just over the ridge. We were never meant to think in terms of planetary scales, let alone cosmic ones. But the moment you try, the whole fabric of your intuition begins to unravel. Let's climb the scale. New York to Los Angeles? About 4,500 kilometers. That's a 6-hour flight. You can imagine that. People do it every day. The numbers are big, but the journey is real. You can look out the window and watch the continents slide beneath you: forest, desert, mountain, ocean. Even the circumference of the Earth, 40,075 kilometers, is conceptually manageable. We've done it. Sailors circled it. Pilots crossed it. In the year 1519, Magellan's fleet set out on a voyage that took 3 years to complete. In theory, you could fly around the world in less than 48 hours today if you could catch all your connections. The point is, these numbers are big, but they still fit inside the story of a human life. Now, let's take one more step. The distance to the moon is about 384,000 kilometers. That's nearly 10 times around the planet. There are no gas stations along the way, no continents to pass, no clouds to look down on, just black, endless black, and a marble hanging in the sky. The Apollo astronauts took 3 days to get there, strapped to one of the most powerful machines ever built, traveling at 11 kilometers per second. That's 39,600 kilometers per hour, roughly 400 times faster than your car on the highway. And still, 3 days. 3 days in a capsule, hurtling through nothing to reach the closest celestial body to Earth. Let that sink in. We can see the moon with our bare eyes. We point telescopes at it. We gave it a name before we had words for atoms or bacteria. It's right there. And yet it's so far away. We had to reinvent physics and engineering just to touch it once. Now imagine this. What if you wanted to go farther? To Venus? Mars? The Sun? Suddenly, even the word kilometer starts to break. It becomes absurd. We're no longer measuring distances. We're counting zeros, abstract digits, symbols on a screen that no longer connect to experience. Let me put it this way. The Earth-Sun distance is about 150 million kilometers. That's a 150 followed by 6 zeros. At Apollo speeds, it would take you 5 months to reach the Sunday, assuming you could survive the radiation and the gravity and, the Sunday. But that's just our backyard. The next nearest star, Proxima Centauri, that's over 40 trillion kilometers away. If we kept using kilometers to measure those kinds of gaps, it would be like trying to measure the width of the Pacific Ocean using toothpicks. It doesn't just feel wrong, it becomes meaningless. That's why astronomers did something radical. They created a new kind of ruler, a cosmic one. Instead of asking, how far is it? They asked, how long does light, the fastest thing in existence, take to get there? And that is how the light year was born. But before we define it, I want to pause here because this is the moment right now where your everyday brain begins to fall behind, where kilometers and hours and travel plans and gas tanks all get left behind, where the scale of the cosmos steps in and says, "You don't belong here, but I'll let you look." This is part one. Part two will explore what a light year really is. Not just the number, but the reality, and by the end of it, you may never look at the night sky the same way again. If you're enjoying this journey through space and time, leave a light behind a like, a comment, or a subscribe. Let's keep reaching outward together. Let's define it now. A light year is the distance that light, the fastest thing in the universe, travels in 1 year. Not a second, not a day, not a season. One entire Earth year, 365 days. Each day with 24 hours. Each hour with 60 minutes. Each minute with 60 seconds. And in every single second, light moves about 300,000 kilometers. Every heartbeat, every blink, every tick of a wristwatch, 300,000 kilometers more. That's faster than anything you've ever seen, faster than anything you've ever imagined. A commercial jet? About 900 kilometers per hour. The fastest car ever built? Roughly 1,200 kilometers per hour. Even the fastest spacecraft we've launched, the Parker Solar Probe, tops out near 192 kilometers per second. That sounds impressive. But compared to light, it's crawling. At that speed, even the Parker Solar Probe only reaches about 0.064% the speed of light. It's like watching a tortoise chase a lightning bolt. Let's try to comprehend this with something familiar. Light can circle the Earth's equator about 7.5 times in 1 second. Let that land. Snap your fingers in that snap. Light could have circled the entire Earth more than 7 times. Or, consider this, light can travel from New York to Los Angeles and back 37 times in just 1 second. We're talking about a speed that bends your sense of reality. And yet, even that speed takes time. Light is fast, but not infinite. This changes how we see everything. For instance, when you look at the sun, you're not seeing the sun now. You're seeing it as it was 8 minutes and 20 seconds ago. If the sun were to vanish instantly, catastrophically, we wouldn't know until over 8 minutes later. We'd continue living in sunlight that had already left the surface of a star that no longer existed. Reality is always delayed. When you look at the moon, you're seeing it 1.3 seconds in the past. Not much, but still, the past. Even radio signals, which are also light, just at a different wavelength, take 1.3 seconds to travel from the moon to Earth. During the Apollo missions, every sentence sent between Houston and the astronauts came with a nearly 3-second gap. They'd say something, wait, hear the reply, wait again. This was the first time in human history we felt the speed of light as a limitation, not as a marvel but as a delay. And yet, this delay is essential to understanding the true scale of space, because when we say 1 light second, we mean 300,000 kilometers. That's about the distance from the Earth to the Moon and 3/4 of the way back. 1 light second, one snap of the fingers. Now multiply that by 60, and you get 1 light minute, 18 million kilometers. Multiply again, and you get 1 light hour over 1 billion kilometers. By the time we reach 1 full light day, we're talking about distances that even our fastest spacecraft haven't touched, roughly 25 billion kilometers. And yet, a light year is 365 of those, 365 light days, each one with 24 light hours, each of those made of 60 light minutes, each of those packed with 60 light seconds, each second carrying 300,000 kilometers. The math compounds quickly. The final number is staggering. A light year equals 9,460,000,000,000 kilometers. Let me say that again. 9,460,000,000,000 kilometers. That's 9 million kilometers. Each kilometer as real, as solid, as walkable as the one between your house and the nearest shop. Try walking it. You'll never finish. Our brains were never meant to handle this. We evolved to throw stones, to judge hunting distances, to find the river by sunset. We can picture 100, we can imagine 1,000. Maybe, with effort, we can grasp 1,000,000. But 1 billion? 1 trillion? Now we're talking in ghosts. Let me help visualize this. If you saved $1 every second, it would take you over 32 years to become a billionaire. But to become a trillionaire, you'd have to save $1 per second for over 31,700 years. That's older than writing, older than farming, older than most of what we call human civilization. And a light year isn't 1 trillion, it's 9 of them. And change, each one made of kilometers, not pixels, not code, not abstractions, kilometers. You can walk a kilometer in about 10 minutes. Now multiply that by 9,460,000,000,000. That's the distance to the nearest stars. Not galaxies, not alien realms, just the next stars. That's why we needed a new way of thinking. Not just a number, but a new intuition. The light year isn't just a tool for astronomers. It's a ladder for the human mind. Each rung takes us farther from the familiar and deeper into the unknown. From seconds, to minutes, to hours, to days, to weeks, to months, to the incomprehensible void between stars. In the next part of our journey, we'll start climbing that ladder, one step at a time, and I promise you, by the time we reach the stars, you'll understand why the light year isn't just a distance. It's a revelation. We begin with 1 second, a single tick, a single breath. In that time, light moves about 300,000 kilometers. It leaves Earth, touches the moon, and then keeps going. In fact, in 1 light second, it travels 3/4 of the way back again. So if you stood on the moon and turned on a flashlight, that beam would return to Earth and nearly complete the round trip in the time it takes you to blink. This is what it means to climb the light ladder. We start small with something almost understandable, and then we keep doubling, stretching, multiplying until reality itself falls behind. So let's climb. 1 light minute is 60 light seconds. That's 18 million kilometers. That's already farther than any car or plane or spaceship you've ever imagined traveling. The sun? That great burning sphere that lights up your life every morning? It's about 8 light minutes away, which means the sunlight that warms your skin, the golden rays that give life to every tree, every blade of grass, every drop of ocean plankton, all of it, left the sun over 8 minutes ago. If the sun were to flicker, to dim, to collapse, or even to vanish, you wouldn't know. Not yet. Not until those 8 minutes had passed. You'd keep living in the light of something already gone. 1 light hour is 60 light minutes. That's over 1 billion kilometers. At that distance, we're starting to leave the inner solar system behind. Planets like Saturn, with its haunting rings, orbit around 1.2 light hours from Earth. When the Cassini spacecraft studied Saturn, every photo it took, every pixel of that world took over an hour to reach us. So, every image you've ever seen of Saturn wasn't live. It was over an hour old the moment it arrived. By the time you saw it, Saturn had already changed, and we couldn't steer Cassini in real time. Every maneuver, every orbital shift had to be pre-programmed and sent days in advance, because when you live on cosmic scales, delay becomes a way of life. Now let's push further. 1 light day is 24 light hours. That's around 26 billion kilometers. At this scale, we approach the realm of Voyager 1, the farthest human-made object in existence. Launched in the year 1977, Voyager has been flying through space for nearly 5 decades. Its mission? To carry a golden record, a message in a bottle, into the deep ocean of stars. And yet, even after all this time, Voyager is still within 1 light day of Earth. 50 years. 17 kilometers per second, and it hasn't even made it 1 full day at the speed of light. From a cosmic perspective, Voyager hasn't left the front porch. 1 light week is 7 light days, about 180 billion kilometers. At this range, nothing human-made has ever reached, not even close. You're now in deep space, a region without maps, without radio chatter, without gravity strong enough to feel like home. Here, the sun is no longer a blinding disk. It's just a bright star among stars, prominent, yes, but no longer unique. If you stood here, somehow surviving the void, you'd see the familiar constellations, slightly warped. The solar system would look like a dust mote lost in a beam of cosmic light. The planets, invisible. Jupiter might be a dot, but Mercury, Earth, and Mars would vanish entirely to the naked eye. And then we arrive at the milestone. 1 light year, 365 light days, 8,760 light hours, over 9,460,000,000,000 kilometers. This isn't just a number anymore. This is a wall, a horizon. 1 light year is the minimum distance between stars. And even that is rare. Most stars are separated by dozens, sometimes hundreds of light years. Our nearest stellar neighbor, Proxima Centauri, is 4.24 light years away. That's the closest. And that means, even if you could travel at the speed of light, which no human ever has, and no spacecraft ever will, you would still need over 4 years just to say hello to the next sun. Let's pause here, because here's what you're starting to realize. As the numbers grow, so does the silence. The gaps between stars are not just distances, they are barriers. Barriers of time, barriers of communication, barriers of imagination. The light year is not just a ruler, it is a revelation, a reminder that the universe is not built to be easily crossed, not by cars, not by ships, not by thoughts, but strangely, light still connects it all. Every beam you see in the night sky, every star that twinkles, every point of light on a dark canvas, that's a message from the past. Light left those stars years ago, sometimes centuries, sometimes millennia, and when it finally lands in your eye, you're not just seeing the universe, you're seeing its memory. In part 4, we'll explore what happens when time and distance collapse into one another, when you realize that to see far is to look back, and that the night sky is a photograph of a universe that may no longer exist. By now, you've probably sensed it. We've been climbing through layers of space, 1 second, 1 minute, 1 hour, 1 day, 1 year at the speed of light. But what we're really climbing through is time, because the farther light travels, the older it becomes, and the deeper we look into space, the further we're peering into the past. Let me show you what that means. When you look at the moon, you're seeing it 1.3 seconds ago. That's how long light takes to cross the gap between the moon and Earth. So every image, every glow, every lunar eclipse you've ever seen, it's already in the past. When astronauts on the moon spoke to Houston, there was always a delay, a 3-second gap in every message. Their words took 1.3 seconds to travel. Our replies took the same time back. Even that tiny delay had consequences. In mission recordings, you can hear the pauses, the space between question and answer. The speed of light, usually invisible, becomes audible. Now go a little farther. The sun? You already know 8 minutes and 20 seconds. So when you look at a sunrise, you're not seeing now, you're seeing the sun 8 minutes older. Every beam of warmth on your skin began its journey before you stepped outside. And if the sun were to change, dim, collapse, vanish, we wouldn't know until those 8 minutes had passed. We would be living in an illusion, a light that no longer reflects reality. Now look outward. The nearest star system, Alpha Centauri, including Proxima Centauri, is about 4.24 light years away. So, the next time you see a simulation of that star, or look at it through a telescope, realize this. You're seeing what that star looked like over 4 years ago. If it exploded, if it dimmed, if it gave birth to a new world, you wouldn't know. Not yet. The light is still coming, and it gets stranger. A bright star like Sirius? Roughly 8.6 light years away. That means when you look at Sirius tonight, you're seeing it as it was over 8 years ago. You're not seeing the present, you're seeing a memory. If you're 20 years old, you're looking at Sirius as it was when you were 11. If you're 40, you're seeing the star from your early 30s. The night sky is not a live broadcast. It's a library of ghosts. Take Vega, one of the brightest stars in the northern sky. It's about 25 light years away. That's a quarter century. So when you look at Vega, you're seeing light that left the star before your smartphone existed, before your most recent heartbreak, before your child was born, before some of us were even alive. The starlight reaching you now began its journey in a world you don't live in anymore. And then there's Betelgeuse, a red supergiant in the Orion constellation, a star on the brink of cosmic death. It sits about 550 light years away, which means if it exploded right now, you wouldn't see it for another 5 centuries and a half. The glow in the sky might already be gone. We might be looking at a star that died during the Renaissance, when Leonardo da Vinci was painting, when Shakespeare hadn't yet written a single play, when the printing press was still a radical invention, and yet it still shines, still visible, still here, because light remembers. This changes everything, because from this perspective, space and time collapse into one another. You can no longer separate where something is from when you're seeing it. The farther you look, the older the light becomes, which means the night sky is not a map, it's a history book. Some stars you see tonight may no longer exist. Some are changing. Some have already exploded. And you? You are watching the light from those events drifting toward you, like echoes across a canyon too vast to cross. When you look up, you're not just looking outward, you're looking backward. Back through years, back through centuries, sometimes back through millennia. And this isn't just poetic, it's literal. A telescope is not a magnifying glass, it's a time machine. When we peer deeper into space, we're seeing the universe as it used to be, not as it is. That galaxy you see glowing in a Hubble image, its light may have left it a billion years ago. That means we're seeing it as it was when multicellular life had just begun to crawl across the oceans of Earth. We are seeing events that predate not just humans, but dinosaurs, forests, and mountains. There is no such thing as the present in astronomy. Every image is delayed, every star is aged, every glow is a signal from the past. You can never know what the universe looks like right now, only what it looked like. And sometimes that difference is profound. In part 5, we'll cross the next threshold from stars to galaxies, from nearby neighbors to ancient beacons on the very edge of the visible cosmos. We'll ask, how far back can we see? And what lies beyond that? We've crossed stars. We've watched light from nearby suns, light born before you were, light older than your language, your family, your entire civilization drift across space and reach your eye like a whisper. But now, we go further, beyond Betelgeuse, beyond Proxima, beyond even the oldest stars visible to the naked eye. We go to galaxies. Galaxies are not stars. They are cities of stars, each one a swirling gravitational cathedral made of billions or trillions of suns. The galaxy you live in, the Milky Way, is home to at least 200 billion stars, and we now estimate that there are at least 2 trillion galaxies in the observable universe. That word observable is important because there is a limit, a wall, a boundary where even light, the fastest thing we know, can't reach us. Not because it's too slow, but because the universe has expanded too fast. Let's explain. The universe is about 13.8 billion years old. That means the oldest light has been traveling for nearly 14 billion years. You might think this means the edge of the observable universe is 14 billion light years away, but it's not. It's farther, much farther. Why? Because space itself has been stretching the whole time the light was traveling. It's like trying to run across a hallway while someone is pulling the walls apart. You keep running, but the destination keeps receding. As a result, the edge of the observable universe is now about 46 billion light years in radius. That's 92 billion light years across. That's not the size of the whole universe. That's just the part we can see. The rest, forever out of reach. Light from those regions will never reach us. Not now. Not in a trillion years. Not ever. So what's at the edge? Galaxies so far away. Their light left them more than 13 billion years ago. Light that began its journey when the universe was just a few 100 million years old. When there were no planets, no stars like our Sunday, no elements heavier than helium, no life, just hydrogen, gravity, and the first flickers of light. When we look at those galaxies captured now in deep field images from telescopes like Hubble and James Webb, we are seeing the infant universe. Baby galaxies still forming, collapsing clouds of gas, igniting for the first time. Light that has traveled across billions of years to bring us a message. This is where it all began. But here's the twist. Even as we look farther and farther, we are also looking older and older. Eventually, we hit a limit. A point where the universe was still opaque, filled with hot plasma, so dense that light couldn't escape. This moment is called the cosmic microwave background, the afterglow of the Big Bang. It's the oldest light we can see, a fossil from when the universe was only about 380,000 years old. Beyond that, darkness. Not because nothing was there, but because light couldn't yet travel. Imagine standing at the edge of an ancient forest, a wall of mist in front of you. Everything behind that mist exists, but the light hasn't pierced through. That's what lies beyond the observable universe, a place we can never see, not even in theory, because the light has not had time to reach us, and some of it never will. Now, breathe. Let your mind try to stretch across that number, 92 billion light years. That's the diameter of our current window, and it's only growing as the universe continues to expand. But what's truly staggering is that everything you've ever known, every person, every planet, every galaxy you've ever seen, all of it exists inside that window. We live in a small island of visibility, adrift in a vast cosmic ocean. And the farther we look, the more we see stars as they used to be, galaxies as they once were, moments that no longer exist, preserved only in light. This is not science fiction, it's observation. When astronomers study galaxies 10 billion light years away, they are literally observing the universe 10 billion years ago. That galaxy may have changed. It may have merged with another. It may have gone dark. It may be gone entirely. But we still see it as it was, because light takes time and space is vast. So when you look at a photo of a distant galaxy, you're not looking across space. You're looking into history. Every telescope is a time machine. Every deep field image is a window into pre-human time. Before language, before Earth cooled, before the moon formed, before stars like the sun even existed. And yet, here we are, tiny creatures, on a small planet, orbiting an average star, in one corner of one galaxy, and somehow we understand this. We measure light that left its source before Earth existed, and we extract meaning from it. We map it, we decode it, we know it. That is what makes this moment extraordinary. In part 6, we'll ask the deeper questions. What does it mean that we are bound by light? What does it mean that all communication, all knowledge is delayed? And most hauntingly, what happens when we try to reach beyond that delay? So far, we've looked outward, measured the distance, followed the light, witnessed the ancient past painted across the sky. But now, we turn inward, because beyond the awe, beyond the wonder and the math, there is a deeper realization we may never hear from anyone else. It starts with light, or rather with its speed. You've heard it already. Nothing travels faster than light. Not rockets, not radio waves, not even ideas. It's not a challenge. It's not a technological hurdle. It's a law, embedded in the very fabric of space and time. And that law, beautiful as it is, builds walls around every world, not of stone, but of delay. Let's say we one day build a settlement around Proxima Centauri, our nearest star, about 4.2 light years away. You send a message from Earth. Hello, how's the weather? Your message travels at light speed, the fastest speed possible, but it still takes over 4 years to get there. Let's be optimistic. They respond the same day. Their reply? Another 4.2 years to return. So, one question, one answer, 8.5 years. That's not conversation. That's archaeology. Now, zoom out. A colony on a planet 10 light years away? A round-trip message takes 20 years. You'd send a hello. Your grandchildren might get the response. A settlement 100 light years away? Now, you're talking 2 centuries just to say, we made it. No real-time feedback, no instant updates, no way to govern, to intervene, to help. By the time your words arrive, the world you're speaking to might no longer exist. This is not fiction. It's not maybe. It's baked into reality. Radio waves are light. Your voice, your signals, your broadcast, they're all bound by this limit. Voyager 1, our farthest spacecraft, is now about 1 light-day away, which means every command we send takes a full 24 hours to arrive, and every reply, another 24 hours back, 2 days, just to say, I hear you, and that's still within our solar system. Now imagine trying to guide a spacecraft at 4 light-years distance. You can't. Not directly. You'd have to plan everything in advance, pre-program every move, build machines that are smart enough to survive alone, to make decisions, to improvise, without help, without confirmation, without any voice from home. This isn't just a technical challenge, it's a philosophical one. Because as you go farther, communication breaks down. But more than that, connection breaks down. The idea of unity, of culture, of shared knowledge, all of it begins to fray when every message is a message from the past. What happens to a colony that waits 4 years for instruction, only to receive advice that no longer applies? What happens when emergencies arise, famine, war, collapse, and help is 8 years away? What happens when people stop waiting altogether? They build their own answers. They make their own laws. They grow apart. Distance becomes independence. And eventually, isolation. We think about the stars as places to go, but they're also places to be cut off. If we settle Proxima, and then Barnard's star, and then Tau Ceti, and then beyond, each will become a world unto itself, not a branch of Earth, but something new, self-reliant, culturally distinct, and perhaps, eventually, unrecognizable. And now comes the heavier thought. If we ever find other civilizations out there, intelligent life, how would we even know? They might live 1,000 light-years away. Their signals, if they sent any, would take 1,000 years to arrive. By the time we received their hello, they might be gone. By the time we replied, we might be gone. This is the Fermi paradox. The universe is vast. The math says life should be common. But we hear nothing. Where is everyone? Maybe they're too far. Maybe they lived and died before we ever looked up. Maybe their signals are already passing through our sky, too faint, too subtle, buried in cosmic noise, and we just haven't noticed. Or maybe they're listening too, waiting, wondering if the silence is permanent. There's something haunting in this. The idea that life could be everywhere, but too spread out, too delayed, too alone, to ever touch. But here's the twist. That silence? It makes us matter more. If we really are the only voices for hundreds of light years, then what we say, what we build, carries a weight nothing else can match. We are not echoes. We are the signal. In part 7, we'll follow that signal into the question of travel. If light is a barrier, can we ever cross the stars? Or are we truly grounded forever? So far, we've accepted one rule. Nothing travels faster than light. But what if we tried? What if we asked, can we go beyond that speed? Can we break the barrier? Could humans or any intelligent species ever travel to the stars in less than a lifetime? Let's begin with what we know. According to Einstein's theory of special relativity, the closer something moves toward the speed of light, the more energy it takes to keep accelerating. But the math doesn't go up linearly. It explodes. The faster you go, the harder it becomes to go faster. Push more, and space resists. Push harder and time begins to twist. At 90% the speed of light, things are already strange. At 99%, time slows dramatically for the traveler. At 99.99%, your journey through time from your own perspective nearly stops. And to actually reach 100% to travel at the speed of light, you'd need infinite energy, which means it's not just difficult, it's impossible, because the universe doesn't have infinite anything. Here's what that looks like in practice. Imagine you board a spacecraft that somehow reaches 99.99% the speed of light. You travel to a star 100 light years away, turn around, and come back. From Earth's perspective, your journey takes over 200 years. But to you, you've aged maybe a few years, or even months. Time dilation, the warping of time itself, has made you a traveler through time as much as space. You leave as one person and return to a world that has moved on without you. This is not science fiction. This has been measured. Muons, particles created high in Earth's atmosphere, travel close to light speed. They should decay in microseconds far too quickly to reach the ground. And yet, they do. Why? Because, from our perspective, their clocks have slowed. Time is moving slower for them. And in the Large Hadron Collider, particles live longer precisely because they are moving so fast. Time dilation is real. It's not an illusion. It's not a glitch. It's built into the fabric of the universe. So could we use this? Could we travel close to light speed and skip ahead in time? Yes, in theory, a long enough journey, fast enough, could carry you thousands of years into the future with only decades passing for you. But there's a catch. You can't go back. This is a one-way ticket through time, and to even attempt it, you'd need a propulsion system beyond anything we've ever built. Because speed is not just about fuel, it's about energy, radiation shielding, heat dissipation, human endurance. Space is not just vast, it's lethal. Still, we dream. We imagine technologies that go beyond the possible. Ideas like wormholes, tunnels through space-time, shortcuts across the universe. Warp drives like the Alcubierre drive, a theoretical bubble of space that contracts in front and expands behind. Hyperspace alternate dimensions where the speed limit is different. These concepts appear in physics papers. They make headlines. They give us hope, but each one has massive problems. Wormholes, for instance. They might exist mathematically, but they'd likely collapse instantly. To keep one open, you'd need exotic matter stuff with negative energy density. We've never seen such matter, and if it exists, you'd need an absurd amount, perhaps more mass than the observable universe. Even worse, wormholes could allow time travel to the past, creating paradoxes. What if you sent a message back in time? What if you changed history? Physics doesn't like paradoxes, and many scientists suspect wormholes simply can't be stable for real travel. What about warp drives? The Alcubierre metric says you don't move through space. You move space itself, contract the front, expand the back, let the bubble ride the wave. Sounds elegant, but again, it requires negative mass, unrealistic energy, and would likely violate causality, the order of cause and effect. And hyperspace? That's pure speculation. No math, no evidence, no reason to believe it exists. It works in movies, but in physics, it's a placeholder for we have no idea. Here's the uncomfortable truth. Faster than light travel might be fundamentally impossible. Not because we're not smart enough, not because we lack creativity, but because the structure of the universe forbids it. Light speed isn't just a limit, it's a boundary condition, a law of nature, like gravity, like entropy, like death. You don't beat it, you live within it. And so, the stars remain far, not unreachable, but separated from us by years, decades, centuries of travel even in our wildest dreams. The galaxy isn't closed, but it is slow. In part 8, we'll shift the lens again. If we can't travel quickly, can we still communicate meaningfully? And more importantly, what kind of future civilizations could still thrive under these conditions? If faster than light travel is impossible, if the stars are separated by decades, centuries, or even millennia of delay, then the next question is this: can a civilization survive under those conditions? Not just survive, but evolve, thrive, grow, dispersed across light years, but still somehow unified? Let's find out. Imagine Earth becomes a spacefaring species, not with warp drives or wormholes, but with patience. We build slow ships. We send robotic probes. Later, perhaps, we send humans, one planet at a time. A ship leaves Earth today, bound for Proxima Centauri 4.24 light-years away. It travels at 20% the speed of light, an optimistic but plausible goal. That means the journey will take over 20 years. By the time the colonists arrive, children born on Earth will be adults. Governments may have changed. Technologies may have evolved. Wars may have come and gone. And yet, the colony begins. Let's say it survives. They grow crops, build shelters, raise children who have never seen Earth, only heard stories about it. And they send a message back. We made it. We are alive. It takes over 4 years to arrive. Earth responds. Another 4 years. A basic exchange. 8 years. So what kind of society survives this? Not one built on speed, not one built on control, but one built on trust, autonomy, and resilience. Colonies would need to function like city-states, self-governing, self-sustaining, culturally independent, like the ancient Greek islands, except the sea between them is space, and the waves are made of time. It would be impossible to run an empire across the stars. By the time laws arrived, the world they were written for would have changed. By the time help arrived, the crisis would be history. Every planet, every moon, every settlement would become its own civilization, shaped by local conditions, local needs, local minds. Some might stay close to Earth's values, others might drift. Different languages, different beliefs, different technologies, different philosophies about life, time, death, and meaning. In just a few generations, they may no longer see themselves as colonies, but as nations, cultures, peoples in their own right. They would look back at Earth like we look back at ancient Mesopotamia, a distant origin, respected, but no longer relevant. So what connects them? What keeps a galactic civilization civilized? Not real-time conversation, not governance, not shared currency or law, but perhaps shared memory, shared purpose, shared archives, shared myths, a distributed civilization, not of instant feedback, but of asynchronous resonance, like sending a message in a bottle across a cosmic ocean, knowing the reply will return long after you're gone. Think about this. We could create knowledge beacons, satellites filled with the full archive of human history, instructions for survival, poetry, mathematics, philosophy, music. Every colony could build upon it, add their own chapters, send their versions onward. Over thousands of years, a cosmic chain of culture could stretch between stars. Not fast, but eternal. Messages wouldn't be conversations. They'd be gifts, legacies. You don't say, "How are you?" You say, "Here's what we've learned. Here's what we survived. Here's what we believed. We hope it helps." Civilizations would evolve in parallel, not in sync. Some may rise and fall. Others may stagnate. A few may leap forward and surprise us. And from time to time, a message arrives, an answer to a question asked generations ago, a voice from another star, long thought lost. Proof that we are not alone in effort, in hope, in curiosity, even if we are separated by oceans of distance and centuries of light. This is not just possible, it's already happening in a primitive form. Voyager 1 and 2, launched in the year 1977, carry golden records, etched with music, languages, greetings, and maps. Not for us, but for whoever may find them. We don't expect a reply, but we still sent them, because hope doesn't require certainty, only direction. Now, imagine doing this intentionally, not as a backup, but as a way of life. A future humanity that spreads not in conquest, but in contribution, that plants seeds of knowledge instead of flags, that measures progress not in territory, but in stories told, mysteries answered, lives made better. That's a galactic civilization that doesn't fight the speed of light, but flows with it. In Part 9, we'll shift from humans to the possibility of others. What if civilizations like this already exist? What if their messages are already on the way? And more hauntingly, what if they came long ago and we're only now about to hear them? The stars are silent. You've looked, You've listened. Still no signal. No whisper. No reply. But maybe the question isn't, why haven't we heard from them? Maybe the better question is, what would hearing even look like across light years? This is the Fermi paradox, named after physicist Enrico Fermi, who once asked during a lunch break, where is everybody? Because if the universe is old, over 13 billion years, and big, over 90 billion light years across, and full of stars, over 200 billion trillion of them, then why don't we see signs? Why don't we hear echoes of alien civilizations, their ships, their cities, their transmissions? Statistically, they should be everywhere. And yet, we see nothing. Let's break it down. If a civilization started broadcasting radio signals just 100 years ago, those signals would now form a sphere 100 light years in radius, expanding outward at the speed of light. That sounds huge. But the Milky Way galaxy alone is 100,000 light years across. So we've barely reached 1% of our own galaxy. And even that tiny fraction, our signals are faint. By the time they've traveled a few dozen light years, they're so weak they blend into the noise of space, indistinguishable from background radiation. So even if someone out there has heard us, they'd need a colossal telescope pointed in the exact right direction, at the exact right moment, listening on the exact right frequency, to pick up our cosmic whisper, and we'd need to do the same, to hear them. Now, add time. What if a civilization broadcasted a signal 10,000 years ago? Maybe it's still traveling. Maybe it's just passing through our solar system now. Or maybe it passed 1,000 years before we built radios. We missed it. What if they're too far? What if the nearest intelligent species is 1,000 light years away? That's a 2,000-year round trip for conversation. Civilizations may rise and fall in less time than it takes for one message to arrive. Imagine shouting across an ocean so vast that by the time your voice reaches the shore, the city is gone. Then there's another possibility. What if they're listening to both sides, silent, both hoping to receive, neither daring to transmit, because broadcasting your location into the unknown has risks. Some scientists call it the dark forest hypothesis. In a dark forest, every creature is silent. Every light, every sound could attract danger, so everyone hides, not out of hostility, but out of caution. In that model, civilizations stay quiet, not because they aren't there, but because they're afraid to be found. Another possibility? They were here, 1 billion years ago, long before us. They rose, they thrived, they vanished, and we're arriving late. After the concert has ended, trying to hear music that's no longer playing. We may be walking among ruins we can't even recognize as ruins. But even with all these possibilities, we still search, because all it takes is one signal, a pulse, a pattern, a burst of structured light, or radio waves, or something we don't yet have a name for, something that says, you are not alone. The SETI program's search for extraterrestrial intelligence has been scanning the sky for decades, listening for anomalies, tracking stars, monitoring planets. So far, nothing conclusive. But every year, our tools get better, our algorithms smarter, our telescopes more precise. And with the discovery of exoplanets, over 5,000 confirmed so far, we now know planets are common, and some of them are like Earth, same size, same distance from their stars, possible atmospheres, possible oceans, possible life. One of the most promising is the TRAPPIST-1 system, about 40 light years away. 7 rocky planets, 3 in the habitable zone. If life exists there, even primitive life, its light is already on its way. And if intelligent life ever emerged, they might have already noticed us. They might be watching. Or they might be waiting for a sign that we're ready. So what would a signal mean? It would not be instant contact. It would not be ships in the sky. It would be a wave of meaning, traveling across decades. It would be data, numbers, images, sounds that took 50 years to reach us. And if we respond, another 50 years to reach them. A 100-year conversation but it would change everything. In that moment, the universe would no longer be silent, no longer empty, no longer ours alone. In part 10, we'll look at the philosophical shift. If we do find life, intelligent or not, what does it mean for us? For our purpose, our future, our story? Because to know we are not alone is to realize that the cosmos is not just a stage, it is a shared home. What happens the moment we hear the signal? Not a spaceship, not an arrival, just a pulse, a burst of structured energy, a pattern that could not have come from nature. Proof we're not alone. And suddenly, everything changes. But not in the way movies show. There's no invasion, no panic, no universal translator kicking in. The change is quiet, slow, personal. It begins not in headlines, but in kitchens, in classrooms, in late night conversations. Did you hear? We're not the only ones. The moment we confirm life beyond Earth, the universe becomes shared, and Earth becomes something it has never been before, a local address. For thousands of years, humanity has looked up and asked the same questions. Why are we here? What is our purpose? Are we alone? Religions have offered answers. Philosophies have wrestled with the silence. Science has kept searching, despite it. But once that silence breaks, those questions return sharper, louder, inescapable. Because if they exist, then we are not the sole center of consciousness. We are one chapter in a larger book. Maybe not the first, maybe not the last, maybe not even the most important. That realization is humbling, but it's also liberating, because for so long, we've carried the unbearable weight of being the only voice. Every mistake we made, every war, every failure, it felt absolute. But now, maybe we're not the only civilization to struggle, to fall, to rise again. Maybe our pain is not unique. Maybe our beauty isn't either. We become part of a broader spectrum, a new category, one of the thinking species. But let's be honest, not everyone will welcome this. Some will feel threatened, some will deny, some will twist it into fear, because once you accept there is another, you must confront the possibility that we are not. The most advanced tears, the wisest hug, the kindest plea, or even the most enduring. It forces a mirror into our hands. Who are we really? Not in our dreams, not in our myths, but in our actual behavior. Would they see us as explorers? Or as predators? As artists? Or destroyers? Would we be proud of what they see? Or ashamed? Because when the sky answers back, we no longer define ourselves in isolation. We define ourselves in relation. And that may be the greatest shift of all, because until now, our divisions made sense. Nations, borders, flags, religions, politics. But in the face of a cosmic other, those differences shrink. Suddenly, it doesn't matter where you were born, only that you were born on Earth. Your skin color, your language, your flag, none of it will register from 40 light years away. To them, we are one thing, one species, one world, one data point in the night. The discovery of another civilization may be the first time we finally see ourselves as human. And maybe that's what we need, a reason to grow up, to cooperate, to survive, not out of fear, but out of awe, because the universe just got bigger, and we're not done learning what it holds. Of course, the first message might not be dramatic. It could be a mathematical code, a map, a cultural snapshot, a recording of music, or just silence, intentional, encoded silence, like a sacred pause before speech. But however simple, it would carry everything, because it would mean intelligence arose more than once. And if it happened there, it could happen again, and again, and again. The silence wasn't proof of emptiness, it was just distance. And if they never reply, if the signal came from a civilization now long gone, that still matters, because it means the cosmos once held thought. It means we are not the first to ask, not the first to build, not the first to reach, and we may not be the last. In part 11, we'll go even deeper to the spiritual, philosophical, and evolutionary meaning of our cosmic identity. What kind of species do we want to become in a universe that contains others? And how do we find purpose in a story that spans light years? The stars do not care what we become. They shine, they collapse, they are born and die and merge and explode, all without ever noticing us. The universe is not watching, but we are, and that makes all the difference. In the face of a vast, ancient cosmos, some might ask, what's the point? We are small, we are temporary, we live less than a blink in galactic time. But that question, what's the point, is precisely what makes us extraordinary, because no other known species has ever asked it. We are the first that we know of to look up and say, I want to know where I come from. I want to know what's out there. I want to understand. We don't just exist. We reflect. We imagine futures that don't yet exist. And then we try to build them. We fight extinction. We rewrite biology. We stack metal and fire into towers and launch them toward the void. Why? Because somewhere deep in the human story is a truth we rarely say out loud. We want to belong to the stars. That longing isn't new. It's ancient, coded in our myths, etched into stone, whispered around fires. For most of history, the stars were gods, messengers, mirrors, mysteries, and now they are destinations. Not because we deserve them, but because we refuse to stop reaching. But reaching isn't enough. If we are to survive, truly survive, not just for decades or centuries, but epochs, then we must become more than what we are, not physically, not technologically, but morally, socially, existentially. We must become a species that can think across generations, act across continents, and feel across light years. That means solving things we've ignored for too long. Greed, war, short-term thinking, systems that reward destruction, cultures that fear difference. These may seem like human problems, but in truth, they are interstellar problems. Because if we bring them with us into the stars, if we carry the old scars into new worlds, then we will only spread fracture, not future. To be a spacefaring civilization is not just about rockets. It's about wisdom, about learning to live with difference, to build without domination, to lead without conquest, to survive without erasing others. Maybe that's the real great filter, the thing that destroys most intelligent life before it reaches the stars. Not asteroids, not plagues, not warships from beyond, but the inability to outgrow itself. So what will our legacy be? Will we be remembered, if anyone remembers at all, as a species that reached for the stars and burned out in its own selfishness? Or as one that learned painfully, slowly, beautifully, how to live with itself before venturing beyond? You see, the stars are not an escape, they are a mirror. Whatever we are here, we will be there. If we are fractured, we will fracture among the stars. If we are wise, we will build cathedrals of light that stretch across galaxies. But the seed begins here. Now, with us, and this is not about utopia, it's about direction. Every choice we make, to include or exclude, to explore or ignore, to create or consume, nudges our trajectory toward extinction or expansion, toward chaos or coherence, towards silence or song. In part 12, we reach the end of this journey, but not with answers, with a perspective, a cosmic vantage point that, once seen, can't be unseen. One that asks not just where we are going, but whether, together, we are willing to become something worthy of the stars. We've measured the light year. We've followed photons across time. We've crossed distances our feet will never walk. We've touched stars that may no longer burn. But now, we return to where we started, to this tiny, flickering place we call home, to Earth, because after all the math, after all the metaphors, after all the silence and speculation and science, there is something profoundly human left, a heartbeat, a question, a quiet need to belong, to mean something, to not be forgotten. The light year is not just a measure of space. It is a reflection of how far a thought can travel, a hope, a love, a story. Because even here, on this fragile world, orbiting a mediocre star, in an average arm of a forgettable galaxy, something miraculous happened. We opened our eyes, and we began to ask. We asked where the sun goes at night, where the moon came from, why stars move, why shadows stretch, why hearts break, why minds wander. And every time we asked, we stepped closer to the edge of light, to the boundary between knowing and becoming. You see, the journey to the stars is not just outward, it's also inward. To understand the cosmos, we had to understand ourselves. That time is not fixed. That space is curved. That light is both particle and wave. That seeing is always seeing the past. That truth is often delayed. That silence doesn't mean absence. And that the universe, for all its darkness, lets us be here, even briefly, even imperfectly. That is the meaning of the light year, not the number 9,460,000,000,000 kilometers, not the speed 300,000 kilometers per second, but what it costs to carry a single beam of light across space, and what it means that we were here to receive it. Every night sky is a message. Every star is a memory. Every photon that enters your eye traveled across ages to reach you. And you, just by seeing it, just by knowing, complete the circuit. You matter because you can wonder, maybe the stars will never reply. Maybe we are alone, but maybe that loneliness is the silence before the song. Maybe the first note was us. Maybe the universe is waiting to hear what we become before it answers. So what now? You return to your life, to your screen, to your room, to your body, small and mortal and messy. But you are different now. You have felt the scale. You have stood beside numbers so large they dissolve language. You have understood that distance and time are not separate, that every moment is a motion, that every life is a flicker. And yet, you are not afraid, because you saw your place in a cosmos so vast, so old, so silent, and you did not vanish. You remained, you reflected, you became cosmic. In the end, the light year isn't out there. It's within us, in how far we're willing to stretch, to think, to love, to wait, to hope across darkness. So next time you look up, remember, the stars you see are real, but they are also gone, and still, their light is here, and that is enough.